Thank you very much for the introduction, and good morning, everyone. And well, first, thank you, organizers, for gathering us all around in such a nice place and giving me opportunity to speak about neutrons. Yes, so if I would summarize the whole talk in a single line, what we're trying to do is to use neutron scattering to get a direct look on how skyrmions are moving inside the bulk of the sample. Before we jump in, I would just mention, I would just mention people involved in the project. So the experimental part of the work has been carried out by our group at Technical University of Munich with the great help of the crew of SANS-1 instrument at FRM2. And after the experiment, we had a lot of help from Achim Roche group. They provided the model for the motion, as you've seen from the Allah's work, and they helped a lot to understand what the hell is going on with the data. And again, there was a lot of nice introductions about the skyrmions, so I will be very brief. We are focusing here on the cubic P20 helimagnets. The prime example of this is manganese silicon, which is probably the cornerstone of bulk materials hosting skyrmions. And this is a typical, this is a typical phase diagram of such a material. And as you see, somewhere within the conical phase, we have a skyrmion phase pocket on the right side near the Curie temperature. And the skyrmion lattice here is stabilized by the thermal fluctuations. So, of course, skyrmions have neutrino topology, and this opens the door to many interesting effects. And we are interested in the spin transfer torque in skyrmions. And, well, conventionally, in the ferromagnetic materials, the spin transfer torque is defined when you push a lot of current through the ferromagnetic material. And as you see, electrons are trying to adapt when passing from one domain to another domain. And at certain critical current densities, they begin to push the domain wall into motion. So there's a lot of interesting applications. We could do that in electronics with spin transfer torque, but the critical current densities are extremely high. It's 10 to the 12 amps per meter. And then it was a big surprise that in manganese silicon, it's just 10 to the 6 amps per meter required to set everything into motion. And there is explanation to that in terms of emerging electrodynamics. When your electron is trying to adapt to the local structure of the skyrmion, or local magnetic structure of the skyrmion, by the Newton's law, trying also to push the skyrmion. And in the end, you have a competition between the Magnus force plus dragging force or driving force of your skyrmion versus spinning force, which tries to keep it in the place. So the prime question of all of this is, how can we control that practically? What internal parameters we can change, like the defects concentration in the material or strength of spin orbit coupling, or external parameters such as AC magnetic field, which can help to push skyrmions into motion. And from our side is, before we want to control the transition, we need to be able to controllably observe the transition as a function of different parameters. And with that, we use the help of neutron scattering. Well, if you jump deep into the theory of neutron scattering, of course, it's a complicated matter, but the practical principles of the neutron scattering is straight simple. So you can imagine yourself as a person in the dark cave without everything, and you see a silhouette in the cave, so you want to know who is that. Maybe like if you're an ancient man and you're seeing a saber bear, saber lion, you want to know who is it. And all you have small rocks around, so you can throw these rocks at the silhouette, and then based on the sound response, so maybe it's your friend and he's just swearing at you for playing a fool, you understand who is before you. So this is a neutron scattering. We have some neutrons this. So we have neutrons which we shoot at the sample, and what we do, we record for different directions. We record how many neutrons per second are scattered in this direction. This is called scattering cross-section. And here below you see the expression for the coherent nuclear scattering cross-section. Coherent meaning that, well, we have scattering events happening all throughout the sample, but we want to, so we record only such scattering events which result in neutrons being scattered in the given direction. So that means they are coherent scattering. And so this is the nuclear scattering cross-section. On the right side, this is the ratio of initial and afterwards neutron momentum. This is the scattering length density, which is how well your sample atomic composition interacts with neutrons. So like for neutron scattering, it's how well your atoms in your sample interacts with neutron. And this is a structure factor, which depends just on the structure inside your sample. So this is a general principle how you measure the cross-section and get information about your sample from the cross-section. But of course, there are many nuances to this. For example, this cross-section is defined as a function of neutron momentum transfer, so the change of neutron momentum and change of neutron energy. Using Fourier transitions, you can, sorry, I don't see the laser point from this point. Yeah. So you can go, we start from this, from the dynamic scattering function, and you can use Fourier transform to transition to the real space, or you can go from energy domain to the time domain and study on a scale of characteristic time scales. Like you can study the lifetime of magnons when you go to the intermediate scattering function. And as example for how many there is a nuance in neutron scattering, I just put here the layout of FM2, where you have 43 instruments, if I counted them correctly, and all the instruments are basically measuring cross-section as a function of momentum and energy. But like there are different ways to measure it in different regions of different values. What's very interesting, if you remember, so we wanted to see how skyrmions are moving with neutron scattering. So we need to go to the neutron scattering in chiral structures. And for that, we are using, we're using coherent elastic, which means there is no energy transfer between neutrons and your skyrmions. And it's a Bragg scattering because we have a well-ordered skyrmion lattice. So for the Bragg scattering, you have, like when you have scattering on the different layers of your crystal structure, and then you get a plane wave of reflection. And well, the way your cross-section is calculated is you have a crystal structure, you need to transform, you need to take the reciprocal image of your crystal structure, so transform it to the momentum space. Then, since it's elastic, the length of neutron momentum never changes, and you can draw a sphere with a radius of neutron momentum. So you put your sphere in a way that it touches the points of your reciprocal lattice. And then when you do that, let's say this is the original neutron momentum vector. The distance from the end of the vector to the points of the reciprocal lattice will give you the momentum transfer vector. And like in the practical scale, it means that we have some real space structures. We transform them to the momentum space. So for helical structures, it's just very nicely ordered spots. And since there is a triangular lattice, you have 6 spots scattering pattern. And this is the Ewald sphere, like here. And what we measure is the cut of the Ewald sphere with a plane, which gives you the detector image. So as you may notice here, actually, we don't see the 6-fold scattering pattern, but we see 12 spots. which in this measurement is due to the fact that you actually have two skyrmion domains and they're tilted from each other. So this is how we measure, and to measure that we went to the small angle neutron scattering instrument SANS-1. Small angle meaning that we have small values of the momentum transfer, which translates to the instrumental resolution of few to few hundred nanometers length scales. So since in manganese silicon the typical size of the typical pitch vector is 20 to 30 nanometers, that perfectly fits small angle neutron scattering. And this is the pictures we're measuring, and we're mainly interested in these two intensities since they should come from the skyrmion lattice. And for example, one of the experiments which showed that the spin transfer torque in manganese silicon really happens due to the skyrmion drift was the measurements by Denis and others. When they applied some current to the sample, they added some temperature gradient to the sample, and then they measured two pictures with current in one direction and opposite direction, and then subtracted from each other. So you see that if the original skyrmion position would be somewhere here in the center, depending on the current, it can rotate left or right. So this is how you can observe the skyrmion flow. But this is a static picture. So we want to go to we want to see how it moves in time. And what we do, we will measure so-called rocking scan. This is a scan of the intensity depending on the angle omega, which is here. So we turn the sample in respect to the neutron beam, and we track the intensity of these two peaks as a function of rocking angle. And from that, you get the understanding. The peak position will tell you where your skyrmion lattice is looking at. The width of the peak will tell you how well your skyrmion lattice is ordered. And for example, the area under the curve tells you what is the phase volume. For example, if your area will change over time, that will tell you that either you're missing some skyrmions or they are destroyed. So how do we measure moving skyrmions? So in our experiment, we add some AC field so that as a result, we have the total field tilting around the original direction by a few degrees. And like to show you how the curve would react, imagine that you have a skyrmion string looking up, like something like this, but imagine it's straight, and imagine that it can instantly follow the field changes for a simple model. So then the red area would be just some deformities of the skyrmion or resolution of your instrument. And if you had just the ideal string, you would have here a delta function, but in the practical experiment, you have usually a Gaussian distribution of the rocking curve. So now we switch on the field, and it begins to move left or right following the field. So the rocking curve just moves left or right following the field. And well, this is a simple model, but like in the practical experiment, you may have change of your peak shape. You can have some instrumental artifacts. You can change. You have change of the you may have double peaks. So you have many changes to the rocking curve you analyze. And one last practical thing is that we don't actually measure the rocking curve simultaneously. It's important to remember that we measure each point separately for the rocking curve. So we fix the angle and we measure the intensity as a function over time and then reconstruct the rocking curve. So this is doesn't change the physics behind the subject, but it's very important to remember because there is a lot of underwater stones and artifacts you can hit when you do your experiment. And a quick word about Isande, because I wanted to advertise a bit of the technique. This is a normal SANS. You can measure almost everywhere, but because you always have the wavelength spread distribution of your neutrons come at different moments of time from the sample to the detector, so your time resolution is limited with the conventional SANS. And typically, I would say you would not be able to go above 50 hertz, maybe 100 hertz in your excitation of your sample. And this can be overcome with the Tisane technique. With the difference of the Tisane technique that instead of normal beam, you have chopper disks, which are very well synchronized with the sample modulation and the detector acquisition system, and that you have a pulsed beam. So if you look on this picture, this is the intensity of neutrons which passes through the chopper. So it's a triangle pulses. And this is something happening in your sample. Let's say it's a structure factor of your sample. And this is the detector intensity following the scattering on your sample. So the idea behind the design is to make a pulse beam with such frequency relations so that any neutron with any speed going on the sample and then the detector, when it hits the sample at a certain phase, it always hits the detector at the same phase of the detector oscillation. This just comes from the geometry on this time-distance diagram. And then it can be shown that Tisane is very flexible in terms of its time resolution, and the limitation of the resolution comes rather from the instrumental constraints, like from the maximum chopper speed. And nowadays you can measure up to 30 kilohertz of the sample excitation frequencies. So now finally we go to the experimental results. This is the previous results done by Sebastian Neubauer and others. So they already measured some Tisane in manganese silicon in Berlin. And this is a scan when you go from the left side of the phase diagram to the right side in temperature at fixed static magnetic field and AC field amplitude. And we apply sinusoidal field to the sample. So you see that when you don't see very much signal here because you're on the border of the conical phase, but when you go to the skyrmion phase, you have the motion of the rocking peak. So the previous curves, the rocking angle is in this direction, and this is the time. So they made several measurements also as a function of AC field amplitude, and they constructed such line where it's this is amplitude of AC field in the units of voltage on the coils, and I think this is the amplitude of the skyrmion motion. So what is important here that you need to apply certain AC field to set it into motion. Like if you apply AC field lower than some critical value, you don't see any motion at all. And then the first question was, when I saw these results, was, right, is there a step-like function or is it continuously increasing? Is there some saturation? And also this was done only in the manganese silicon, and we wanted to make a deeper analysis and try different compositions like CSO or doped samples. So we started this experiment now trying to reproduce the results at Berlin with manganese silicon. And this is the rocking peaks moving, trying to follow the field, which is shown by the dashed line. So you see again, at some field values, you apply AC field, but the rocking peak doesn't want to move until you reach some critical value of AC field. And this is the amplitude of the AC field tilting in terms of degrees. So there is a certain threshold, and when you go through this threshold, you still have the amplitude of your rocking peak motion is always smaller than the amplitude of the field tilting. So skyrmions are never able to completely follow the field, as in our experiments. And well, it's not so obvious here, but we checked that there is no changes in the rocking peak area, meaning that we don't lose any skyrmions, or there is no skyrmions created or destroyed. And this would be a very interesting result, since you see two rocking peaks here, meaning that you have breaking skyrmions into the domain, so something like this. But unfortunately, this was an instrumental artifact. We spent half of the year arguing with Achim, is that true or not? He was right. So now, since we were provided a very nice model how the skyrmions moved. We tried to make some simulation in this model and see how the skyrmions, how the experimental results based on the model would look like, and what should we expect from the data in order to better understand the data. So I will just a quick recap of what Alla said, that we have a skyrmion string, and skyrmion string is originally pinned at the center, and the originally motion starts at the end of the strings, like top and bottom. And motion at the end of the strings is determined by the competition between the driving force and pinning force, and the rest of the string tries to elastically follow the ends. So when you start moving the field, it looks something like this. So you see that even though skyrmion is already trying to move, there is a central region which is still pinned. So the overall skyrmion, that the whole structure can be still pinned, but you will be able to see some motion on the rocking peaks, on the rocking curves. And within this model, there is two transitions. First transition is when you just see any motion of the skyrmion, like just you see any bending of the skyrmion tails, but the center is still pinned. And the second transition is when the whole skyrmion is unpinned and you have either walking phase, or it's just like without the current, it's probably just wiggling around, or it can be running. And translating this picture to the rocking curves, it would look something like this. So this is the rocking curves as a function of time. So this is the time within the cycle of oscillation. And you see that this is the rocking peak position, which moves trying to follow the field. And this value is the intensity at the center. So the intensity at the original field direction. So in the rocking curve, any intensity corresponds to a part of the skyrmion phase volume which is looking in a given direction. So this value will tell you how much of your skyrmion is still looking in the original field direction. And this part of the rocking curve will tell you how much of your skyrmion phase is moving following the field. Or in other words, so this translates to the tails, and this translates to the center. And what we do, we track the amplitude of the skyrmion peak motion, and we track the minimal intensity at the center, which would give you amount of skyrmions which are always looking in your static field direction, which are always spinning. And we plot them on top of each other, like here. So this is the amplitude of skyrmion rocking peak motion. And you see that at certain critical threshold, you begin seeing the motion, and then it's linearly increasing. So we are not able to reach any kind of saturation of this curve comparing to the old results. And this is the intensity at the center, which tells you how much of your skyrmion phase is still pinned. And then it begins dropping down right when you begin seeing any motion. And well, in theory, it should drop linearly. We don't see it here, but but it's most likely that the smooth transition is due to some instrumental resolution problems. So there is right now no reasons to not believe that it drops down linearly or close to linearly. So we will determine the first transition as this point and the second transition as this crossing. And now we can do that for different samples. So what we were looking at manganese silicon, which is metallic sample, doped samples, which introduce amount of defects in your material. And sorry if I'm wrong, but I read that this is a semiconductor behavior. But if you correct me, that would be good. So I understand that they behave like iron cobalt silicon, which is semiconductor. And the copper selenium oxide is insulating material. And you see, like already, that for different materials, you have different unpinning transitions, which is all right, because the materials can have different pinning forces. For example, like if you add just 2% of iron to the manganese silicon, you're already creating a lot of defects in your material, which will try to pin the skyrmions to the defects. So that's all right that you have such a step of your critical threshold. And what is interesting that for dope samples only, like here, you first see some increase of your skyrmion intensity before it starts to move. And from the results, we understand that, well, there was an analogy with with a plate of sand. And like when you shake the sand a little, it can help your sand to order a little bit more. So in this way, we apply AC field, but we don't move the skyrmions, and little shaking helps skyrmions to overcome some pinnings to order more into the lattice, hence giving the increase of the intensity. And well, there is one result which we didn't expect to measure, but we accidentally measure one sample for 2 frequencies. And you see that 2 curves, one curve here and one curve here, well, they are different from each other. So they are like the distance between the 2 curves is more than we would expect just from the instrumental resolution, meaning that there is some frequency dependency of your unpinning. And when you go to larger frequencies, you have to apply larger AC field amplitudes to drive your system into the motion. If you will have questions about this, I have additional slide. What we wanted to claim here is that looking at the curves, and if you forget the fact that there is perks of the doping system, the oral mechanism of skyrmion and pinning looks like it's a universal mechanism. So what we tried to do is to fit all the curves on top of each other using some scaling parameters. So Bmax and minus Fmax is competition of the driving force minus pinning force. And this is how it looks like. So there's, of course, there is some discrepancy between the curves, but well, this particular picture is a work in progress. So there is a lot of, unfortunately, steps where you can introduce the instrumental error, which would lead to the discrepancy between the curves. So what else to be done in this? Unfortunately, we don't have neutrons now at FM2, but we hope that one day we'll get them back. And there's a lot of plans which we could measure. For example, there is a second skyrmion phase at low temperatures, which has different stabilization mechanism. And it would be interesting to map out the transition between the 2 phases and see how the motion within the low temperature skyrmion phase is different from the high temperature skyrmion phase. And another thing what we wanted to do is a deep analysis of the motion. So this is an example from 2011 when they measured low frequency excitations of the vortex lattice in the superconductors. And you see that in contrast to our motion, this is a very step-like motion here. So the question was whether can we see that in skyrmions as well, or in skyrmions it's more like a sinusoidal kind of motion. And to answer for that, we will need to tune the instrument differently to get more time resolution at cost of intensity. But we should be able to do that. And if we can do that, we can also measure this transition time, which in theory should give you some skyrmion relaxation parameters. Yeah, so now we're waiting for skyrmions to do that, for neutrons to do that. So that's the summary. I hope I managed to advertise a little your Tisane technique, which can give you the insight in your inside of your material magnetic structures with a time resolution up to 30 microseconds roughly. And with that you can measure different structures. You can measure skyrmions, helical structure, conical structure, and many others. And what we did, we observed 2-stage transition in different materials. And what our claim is that the transition mechanism is universal between different materials. That's it. So thank you for your attention.